Hello and welcome to the wolfSSL live webinar SM Ciphers presented by Senior Engineer Sean Parkinson. My name's Kristen and I will be moderating the webinar. All attendees will be in listen-only mode. If you have questions, please use the Q&A box. We will also host a Q&A session following the presentation. The webinar will also be recorded and made available on our YouTube channel shortly after the presentation. And I also invite you to follow us on Twitter at wolfSSL, as well as our other socials. And also feel free to email us if you have any additional questions following the webinar. And now I'd like to just give a brief company overview before we move to the technical presentation. wolfSSL was founded in 2004 by Todd Auska and Larry Stefanik when they realized there wasn't an open source dual licensed embedded SSL library available. OpenSSL existed at the time, but there was a demand for an alternative that was easily portable, smaller, faster, available under a clear commercial license, was equipped with clean and modern API, and offered a commercial style developer support. wolfSSL was born into this market need with an OpenSSL compatibility layer. Today, wolfSSL secures over 2 billion connections. We have more than 1,000 OEM customers and dozens of resellers. wolfSSL is made up of over 50 dedicated employees, most of which are engineers. This progress is, of course, supported by a strong partner network that we're proud of. Since the beginning, our engineering team has developed several embedded security products, including wolfCrypt with DO-178 support, FIPS certification and a FIPS ready offering, MQTT up to the V5 spec, SSH v2, TPM 2.0, a secure bootloader known as wolfboot, as well as Java wrappers and JSSE support, and commercial support for curl. All of these offerings are accompanied by a thorough maintenance and support plan up to the 24/7 level. We also offer full service consulting. And now I'd like to turn it over to Sean to talk about SM Ciphers.
Thank you, Kristen. So today we're going to talk about the SM Ciphers, the Chinese ciphers. We've recently added to wolfSSL. I'm going to give you a bit of background on what the SM ciphers are, some of the terms that you will come across, so that you can understand what I'm talking about when I'm referring to how we put it out into wolfSSL. Note also that we have a TLS implementation that uses the SM ciphers, so I'll go into a bit of background on that as well. And then I'll go on to describe when to use the SM ciphers, how to do it with wolfSSL, and any future work that we are planning to do. So SM stands for Shanghai. I've apologized. I have no Chinese background, so I don't know how to properly pronounce it, but it's just a name as far as I can find out. It's not actually translates to anything particular. It's just a nice name they gave it. And the SM ciphers are Chinese national standards. And that means that over the years, and some of these were developed quite a long time ago, the Chinese nationals, on behalf of the Chinese government, created these ciphers that were different from what else has been out there, but similar, to have China-specific algorithms that can be used for Chinese products in China. So there's three algorithms that we've implemented. There's the SM4, SM3, and SM2, and they are a symmetric cipher, hash algorithm, and elliptic curve, plus a signature scheme that's goes with the elliptic curve, which is different from the normal one. And if you're going to be using the SM ciphers, you must use all of them together to be compliant. So that means you can't mix and match use a different symmetric cipher algorithm. You have to use all three, the SM2, SM3, and SM4 in the application or in the TLS handshake together. So the SM4, there's a bunch of standards there that I've listed, but the GBT ones are the Chinese cipher, Chinese documents, China documents. So I'm just putting these up here just in case you see mention of these standards and you want to know whether we're compliant with them, and we are. So the GBT one is the China one. The ISO one is a list of different algorithms, but it is in that list, the SM4 algorithm as and described. There is in the IETF a draft which is expired. So all of these ciphers have been submitted to the IETF, but none of them have actually been standardized. But I've listed the draft just so that you can get an idea of the standards. So it's a symmetric cipher, and it is very similar to AES in its construct, in that it has an S box and a nonlinear transform to help mix up the things. Notably, that it is only a 128-bit key size. So AES has 128, 192, and 256, though mostly you'll only see use of 128 or 256. And the descriptions of SM4 only have a 128-bit key size, which means 128-bit security. With that cipher, you can use any kind of mode with that. That goes with AES or some of the others, including ECB, CBC, CTR, GCM, and CCM. So typically you'll see CBC being used. That going forward, people have stopped using that one and are typically using GCM because it's an authenticated cryptographic algorithm. But you can also use the counter mode if you want, and things like that. So where would you use it instead of AES or CHA-20? SM3, now this is the hash algorithm. There's the standards. Once again, there's a draft in the IETF, which has been expired, so it's no longer being pursued. And the algorithm itself, the construction of the algorithm, it's similar to SHA-256. One thing I did note when I was implementing it was that it has more sort of internal dependencies there, so the data dependencies, to make it what looks a little bit more secure, but also a little bit slower. So, you know, I have to be clear about this. I'm not a cryptography expert in terms of security research and stuff like that. So all I can talk about is my experience in implementation. But it does seem to be as secure as SHA-256. Once again, they only have 128-bit security level, so it's only a 256 variant of the hash in SM3. And so when you use it, you'd use it instead of SHA-256 or SHA-3 Typically, it's people are using SHA-256 these days, and SHA-3 isn't being used much. So you would replace SHA-256. SM2 is the block cipher, is the elliptic curve cryptography part. So it uses the same algorithms for doing the elliptic curves, but they define their own elliptic curve itself. So it's the prime number, the A and B parameters, which comes with an order, and there's a base point which they've generated themselves. So they've chosen a prime to be specifically fast, but it's different from the NIST P256 one or the SEC P256R1 curve. The performance of that prime number in terms of when you implement it, it's not much different from the NIST one. It's just apparently they wanted their own one for whatever reason. Now, for Diffie-Hellman key exchange, you can use the same algorithm. There's not much variation you can do in there anyway, so you just do that. So there is, in our implementation, two ways you can do it. You can use our APIs, or you can just use the standard ones with the right private key. The signature algorithm, on the other hand, is different. So while you could use the curve with the standard ECDSA signature scheme to be compliant with the standards for the China, then you will have to use a different algorithm, which we've implemented. So the R and S is calculated differently, and while it looks fine, the reason they've done this is to actually make it simpler. That means that there's multiple inversion operations that need to be done for ECDSA, and specifically for the verify, by using the maths that they have, you don't need that inverse. And also there is in the inverse, there is a use of the private key. So that means that instead of using a temporary value, it's more amenable to doing pre-calc. So if you pre-calc the value on that you're dividing by doing that inverse, you can reuse that across all signature operations. So where to use it? Anywhere you could use SEC P226 R1. Note, of course, that there are 384 and 521 versions in NIST, and they are higher strengths, but SM2 is just the P226, the 256-bit curve, and there's no higher security ones. So 256 SM2 curve is 128-bit security and matches the other hash and cipher. So how does that work with TLS? So there is a TLS 1.3 standard, RFC 8998, and it has been obviously approved, and it describes the cipher suites and how to construct, do a handshake with TLS 1.3 using SM4, SM3, and the SM2 public key algorithms. So there are some, slight changes that have to be made to the handshake in order to be able to support SM2, SM4 GCM, and the SM3 hash are pretty much, drop-in replacements. There's nothing much you have to do. So there's only 2 cipher suites, SM4 GCM with SM3 and the CCM with a variation. And that's matching how the AES GCM with SHA-56 and the CCM with SHA-56 works as well. The TLS 1.2, on the other hand, there is no official standard for that. I've looked around on the internet trying to find something that would say how to do it, but I had to go on a Chinese implementation that's publicly available to determine what to do. In actual fact, that they only supported some of the cipher suites, so we have gone ahead and implemented stuff that's not otherwise implemented as far as we know. For certain, OpenSSL does not support SM cipher suites in either TLS 1.3 or 1.2. So some of these things are being done for the first time for the public to see and use. So the cipher suites we've added ECDHE, ECDSA, so elliptic curve cryptography using SM2. And we check that you are using SM2 with the SM4 CBC and SM3, GCM and CCM. So CBC is fine. There are some questions about whether you should be using CBC going forward. So do use GCM or CCM if you can. Now, because it's not actually a public standard, there's no actual defined values for what the cipher suites should be when you're creating the messages for the TLS handshake, TLS 1.2 handshake. So that I've just used, wolfSSL has just used the values that were discovered in the Chinese implementation, and they are in a private range. So interoperating with other interesting implementations where they also use private range values for their special cipher suites could be interesting, but it's likely that these values will be unique. So From a recommendation perspective, though, you should be trying to use TLS 1.3 with the SM Ciphers. That will be the recommendation, given that there is standards for that have been approved and that are publicly available implementations for other than just the wolfSSL. So when to use the SM Ciphers? RIM required by jurisdiction. That seems to be the only key reason to use the SM Ciphers. They are in performance, there's not much difference for the SM2. It may be slightly faster in verification. SM3 is just slightly slower because it's got those extra data dependencies in the algorithm, while the SM4 at the moment is significantly slower. But having said that, there are cryptographic instructions available on some chips. So for the AR64, I found that there are in the standard for the chipsets, they have listed SM2, SM3 and SM4 instructions that are specific to those algorithms. And you can have used those, and they're available in the code base at the moment. And I've tested that with a simulator, but I haven't actually seen a real life implementation on a physical chip, so I don't know what their performance is going to be like. So from the C perspective, if you want a small code and you're in an embedded system situation, then yeah, SM4 is probably slower, so you don't really want to be using it, and the SM2 is on the actual startup, so you won't get that much benefit from it. So use it where you have to. Other countries, say US, may not like people using these ciphers. I'm not aware of what the situation is, but they tend to want to use the ones that are localized. So wolfSSL, what do we have? We've got implementations of the SM2, SM3, and the SM4 with these modes. The ECB, because that was simple, it's just going to work because that's what the SM4 is about. It's just the raw cipher. We also added the CVC, counter, GCM, and CCM so that they could work with different cipher suites in TLS. And we have C implementations, small variations as well, so that you can have small code size as well as small code usage, memory usage. There's also, as I mentioned, ASM code for AR64, which uses the cryptographic instructions as defined by the standards. I'm assuming that they will be quite fast then, the SM3 and SM4 algorithms. I've also implemented SM3 on the Intel x64 assembly code, just because it was something that was keen for me to do, to see the difference between the performance, and yeah, the performance is about the same. So for embedded systems, the C implementation's there and ready to go. What have we done for the TLS? Well, we've got the TLS 1.3 support for those two modes of SM4, and we've got the cipher suites that were mentioned above before for TLS 1.2. I can't think of any other cipher suites you could possibly do apart from static ECDH, but that cipher suite, those type of cipher suites have been clearly named as weak, so there's seemed no point in implementing those. We also had to implement certificates for SM2, and there came to be two different variations of the certificate, where the OIDs, the object identifiers for what the public key looks like, came in two flavors, one with one OID that was a generic public key and one with the SM2 OID. There's also private keys and public keys we had to do, so we can load those from SM1 encodings. And we're looking at to see if there's any implementations of or any keys out there that don't match what we've seen and implemented to. And we will in the future make sure those work. So how do we build wolfSSL with SM ciphers? Due to legal considerations, it was decided that the implementations of the SM ciphers needed to be in a different Git repository. The wolf SM repository is where we've kept this. We've put all these implementations, and it is public. It's not restricted at all, so that anybody who wants to try it out can try it out. To install the code, you just have to git clone the wolfSSM and the wolfSSL repositories next to each other, and then copy the code from wolfSM into the wolfSSL. We've created a nice little script there that will do that automatically for you. You just have to change into the wolfSM directory, and as long as wolfSSM and the wolfSSL are together in the same directory, then it'll just copy it in. And you can see the README for manual instructions if you're not on a box where you can use install.sh. It's just a few files that need to be copied into a wolfcrypt source directory and into the header directory. So it's not much at all. To configure, you do need to add a couple of extra options to the configuration line, or add some extra defines if you're not using the configure system. So for SM2, you must enable ECC, of course, since the SM2 stuff is ECC. And then you need to enable the SM2 feature. What this does basically is just define wolfSSL SM2 and wolfSSL base 16, given there's some need for that in some specialized signature handling. The SM3, similar kind of thing. You can just -- enable SM3 and the hash algorithm will be included. But there's also a small option, and that will compile up the small implementation of the C code. So you just it'll hash define wolfSSL SM3, and optionally you can define the small wolfSSL SM3 small to get the small code size built. And SM4, we have a separate configuration for each mode. So typically, you don't want all of the algorithms available. You only want, say, GCM or CCM and GCM, or maybe just CBC. So you just enable the ones that you want. So to enable SM4 for the CBC mode, then that's the configurations lines you have to use. Enable SM4 CBC, -- enable SM4 CBC equals small if you want the small code as compiled up. And what that does is create those defines. If you want it to be SM4 GCM, enable SM4 GCM. And if you want the small code, just put equals small at the end, or define wolfSSL SM4 GCM. And to get the small code compiled, you just use wolfSSL SM4 small. You don't have to specify the mode for that. So how do you use the SM ciphers in wolfSSL? So there's kind of two different ways you can do these. You can use them. You can use them as individual algorithms, or you can use them in TLS. So first of all, I'll go through how to use SM3, the algorithms themselves individually. So SM3 is the hash algorithm. So you want to hash data. So the APIs for doing that are, WC init SM3 to initialize an SM3 object, WC SM3 to update to take the digest the data to digest, SM3 final to calculate the hash, and the free to dispose of any dynamic memory. For C code, there's not going to be, at the moment, there's no dynamic memory, but going forward there may be, so it's best to call the free even though it doesn't do anything at the moment. So this is the standard hash pattern of APIs. We also have a WC hash API that you can specify the algorithm you want, and it will do the calls to the specific algorithm internally, and you can use that as well. We have updated that to support SM3. SM4, so for CBC example, you're decrypting and encrypting and decrypting data. So the APIs are initialization. You have to set the key and then set the IV, which is different from AES, but you do set them individually. And then it's called CBC encrypt or CBC decrypt, and call the free to once you've finished. The C implementation doesn't have any direct data, as I remember, so that there's no need to do that. But as I said, going forward, there may be a need for that, to call that. So it's pretty simple. You just setting the key in the IV separately before you do the encrypt and decrypt, or decrypt. Now for GCM, it's pretty similar to the AES GCM way of doing things. Initialization, set the GCM key. GCM has a special way of dealing with the key, so we need to have a separate API for that. You do an encrypt, or you do a decrypt, and you do a free. All pretty simple. And for SM2, there are specific APIs we've included that make sure that you are using an SM2 curve. So for the ECDH, you've got two operations that you need to do. You need to create a key, create a new ephemeral key, and you need to create the shared secret with the peers key. So you initialize an ECC object, which is the generic API. There's no SM2 version of that. And then you can call SM2 make key, and then to create a key pair, private and public key pair. And then once you've received the peers public key, you can call SM2 shared secret. If you use WECC make key EX, it does have the option of specifying the curve ID, and you can specify the SM2 curve if you want, and then you can just use WECC shared secret to do the operation with the key. You don't have to use the SM2 versions. Now for the sign and verify operations, it's different. You do have to use the SM2 APIs. So once again, it's a generic WECC init, and then you need to load up the private or public key, depending upon the sign or the hash operation you're doing, using the standard ECC APIs. Then you can sign the hash with SM2. There are other kind of complications to that, which I won't go into here, but we have all of the APIs to handle all the different ways of dealing with special data being used. So it does this SM2 sign algorithm and SM2 verify algorithm as required. You can try to it is possible to use the ECC sign hash function, and it will produce signatures, and you will be able to verify the signatures, but it just will not be a conformant signature. So moving on to the TLS layer. So how do we use that? Well, there's no real magic. You just have to specify the string TLS SM4 GCM SM3 or CCM SM3 for TLS 13, and the other strings listed there below for TLS 1, 2. All the magic happens behind the covers, where it will convert that into the appropriate numbers to go into the handshake. The default builds, the default cipher list will include those algorithms if you compile with it. So if you are having different domains where you're creating ciphers, creating connections with one set of ciphers that are not to have SM in it, and another set of connections that only have SM in it, then you'll want to set the cipher list explicitly so that you will guarantee that you will get the cipher suites that you expect on the connections. But do note that once you set an SM2 certificate and private key, then you can only do these cipher suites. So there's kind of a forcing you into that using those cipher suites explicitly anyway. Equally, if you don't use SM2 certificate and private key, and you use a P261 one, then you can't, it won't negotiate the SM cipher suites. So future work, what else are we going to, what is not there that we want to have, and what are we looking forward to doing in the future? So we have assembly optimization for some things, very limited amount at the moment, and there's more that we'd like to add. So in particular for the maths, we haven't got a optimized implementation for that that's specific for the SM2. And there is some work that has been done previously that we can leverage so that we can have a very fast implementation of SM2 that's comparable to the very fast P226 implementation that we have. So that would be for ARM2, the ARM32, and AR64 and Intel x86-64, that specialized maths implementation. Also, we'd like to look at SM3 and SM4 on these architectures. Even though there's AR64 instructions, cryptographic instructions, they're not necessarily going to be built into the chips that are deployed. So we need to have assembly optimized versions for those chips as well. Probably using like the Neo instruction set, so that can speed things up. We can base our assembly optimized versions on what's been done for AES and SHA-256. So it's just a bit of work to understand the differences and what we can and can't do. Let us know what you would like to see us do next in terms of what chips you're using and what optimizations you need. If you're totally embedded and need it to be really small code, then you can be, we expect people to be happy just with the C implementation. But as always, we find customers need to have the fastest implementations. So being able to target the implementations that customers need the most is important for us, so that we know where to spend our time on to get it out as fast as possible. So that covers all of the work that we intend to do with the current algorithms. There's another cryptographic algorithm called ZUK, based upon the name of the person who designed it. It's a stream cipher, and it is part of a 3GPP standard. So at the moment, we haven't started working on that, but we are definitely looking to do that. And if we have customers that are needing that, they need that for a standard, or they need a stream cipher that's China specific, then we will work on that. So let us know if you have a need for that. Apart from that, we are going to be looking at interop to see if, as any implementations come up, that it does interop. We are interoperating with the Chinese implementation that's public. The TLS 1.2 one is not quite there though for them. They did some shortcuts that meant that they're not actually doing the protocol properly. And I had to modify the code to get interoperating, but we will continue to be looking to other implementations out there to see who and when, who has implemented and made the cipher suites available, and we'll interoperate against that. Okay, so that's it for the slides. Are there any questions?
Thanks, Sean. If anybody has any questions, feel free to raise your hand if you'd like to ask it directly, or go ahead and type it in the Q&A section. Okay, let's see. We've got one. I just unmuted you, Sean. There's another Sean.
Oh, hi. Hi, Sean. It's nice to hear your voice. Status, did you mention anything about the OSCCA certification?
No, I haven't. I'm not across our efforts to do the certification or anything like that. Can you sort of, for those people who don't know what it is, could you just give a brief description of it?
Oh, yeah. There is a agency, that kind of ministry that functions like, I guess, a NIST or FIPS that certifies cryptography products and devices, that especially ones that have been designated as critical networking equipment, for example, and they require certification of the crypto ciphers. I think you would be a good candidate for that, since your implementations are open source.
Yeah,
but
sure.
I don't know. I guess I was just checking to see if you've had any progress with OSCCA, the OSCCA in China towards certification of your implementation.
Yeah. So as I said, I'm not across our efforts to do that, but that is something that we are looking at, because we know that customers will need to have it certified. And as customers, talk to us about that, we will definitely be promoting, moving ahead more quickly as customers have actual dates that we need to meet the standard by, to or get it standardized by, kind of thing.
Wonderful. That sounds great. Thanks, John.
Okay, thank you.
All right, are there any other questions? Like I said in the beginning, we will be posting the webinar on our YouTube channel. So, and if anybody would like slides or has any questions, please feel free to reach out to us. You can reach us at support@wolfSSL.com or fax@wolfSSL.com. And so I guess if there aren't any other questions, thank you, Sean, for presenting, and thanks everyone for joining.
Thanks, everyone.
Have a good rest of your day. Bye-bye.